Okay, let's start with this one. So here in this problem, we have air is compressed polytropically, which means that we already know that the process follows a path PV exponent n is equal constant. We are given the value for n, which is 1.3. And we are also given the initial temperature, T1 is equal 17 degrees C, and the initial pressure, P1 is equal 100 kilopascals. We are also given the final pressure after compression, which is equal to P2 is equal 500 kilopascals. We are given the gas constant for air, we are given CV and CP values, and we are asked to calculate the final temperature in Kelvin, this is T2. We are also asked to calculate the work, and we are also asked to calculate the change in internal energy, meaning U2 minus U1. Okay, this is problem 4.1 on our problem pack. And as usual, it's good to sketch the two states. So we have state 1 and we have state 2. We have a piston cylinder assembly. So the piston is at a certain position to start with. We know that we have air inside, and we are given the temperature T1 equal 17 degrees C, and we are also given the pressure P1 is equal 100 kilopascals. Then we have a compression process, so the piston will move down to a new position. And what we know the pressure now increased to P2 is equal 500 kilopascals. And the process between state 1 and state 2 follows a polytropic process. PV exponent 1.3 is equal a constant. So what we are asked to calculate T2, the work, and the change in internal energy. So let's start with calculating the final temperature. So computation of T2. So what do we know? We know that we have a polytropic process, so we know that PV exponent 1.3 has to remain constant. Okay, what does it mean? In the context of our process between state 1 and state 2, this means that P1, V1, exponent 1.3 is equal to P2, V2, exponent 1.3. So therefore, we can write, so this will be equivalent to P1 over P2 is equal to what? Is equal to V2 over V1 exponent 1.3. But we are dealing with air, so this is an ideal gas. So we can replace the volume with the function of temperature, because remember, we are looking for the temperature here. So but PV is equal mRT. Therefore, the volume is equal mRT over P, that we can replace here. So this will give us P1 over P2 is equal to what? Is equal to mRT2 over P2 over mRT1 over P1 exponent 1.3, right? So now we have the same mass, okay? The mass doesn't change here. And it's the same gas, we still have air, so this one will disappear. So this will lead, so this is equivalent to P1 over P2 now is equal to what? Is equal to T2 over T1. Remember, we are looking for T2. Exponent 1.3 cross P1 over P2. So here they're reversed over 1.3. So now we can calculate from here T2. So this will give us T2 is equal to, I will write it as T2 over T1 first, P1 over P2, exponent 1 minus 1.3 over 1.3, right? So we brought this here, okay? So this is 1, exponent 1 minus 1.3, okay? So then actually all this divided by 1.3. So this is our 1.3 here. So this is equivalent to say now that T2 is equal to T1 cross P1 over P2 exponent 1 minus 1.3 over 1.3. We have T1, which is equal to 17 degrees C. We have to convert it to Kelvin. We have P1, which is 100 kilopascal. We have P2, 500 kilopascal. So we have all the ingredients to calculate our T2. So it's equal to 290, this is our 17 degrees C, cross 100 over 500, exponent 1 minus 1.3 over 1.3. Okay, and this will give us ultimately a temperature of T2 is equal to 420.4 Kelvin. So here now we can write that T2 will be equal to 420.4 Kelvin. Let's move on now to the second part of this problem. In part B, we are asked to calculate the work between state 1 and state 2. So computation of the work 1, 2. I like actually to write it this way. So W12, meaning this is the work between state 1 and state 2. So what do we know? We know that the work 1, 2 is equal to the integral between 1 and 2 of PdV. And here we know that there is a relationship between P and V. PV exponent 1.3 is equal constant. If you remember well, in class we derived this, and we showed that this will have the form of P2 V2 minus P1 V1 exponent 1 minus n. So this will give us, this calculation in function of the volume would give us the unit in kilojoules, but we are asked specifically to get this in kilojoules per kilograms, okay? Now look at this P2V2, since this is an ideal gas, we can write it as mRT2, right? And the same thing here, P1V1, this is mRT1. So, which means we can write now the work as mR simply T2 minus T1 over 1 minus n. And we can divide by the mass. So the work 1, 2 now, this will be in kilojoules per kilograms, is equal to the work 1, 2 over the mass, and it's equal simply to the gas constant cross T2 minus T1 over 1 minus n. So we are given the gas constant. We just calculated T2, which is here. We are given T1. We are given the value of n, which is 1.3. So we just have to plug the value to get our work. So this will be equal to 0.287 cross the 420.4 minus 290 over 1 minus 1.3. And this will give us a value which is minus 124.7 kilojoules per kilograms. And you see, it does make sense, right? The sign here is negative. Why? Because we have a compression process, okay? This is a work N. So it has to be negative. You are actually providing the work to compress the gas. So the last step, that will be right in here. This is C. And we're asked to calculate the change in internal energy. So computation of the change in internal energy. So here we have to calculate U2 minus U1. So this is U2 minus U1, or our delta U. And we know that this is equal to the integral from 1 to 2 of CV delta T. If we assume now that CV remains constant, so this will be equal to CV integral from 1 to 2 of delta T. And this will give us simply CV T2 minus T1. We are given CV, we are given T2, sorry, we just calculated T2, and we are given T1. So we just have to plug our values, and this will give us 0.723 cross our 420.4 minus our 17 degrees, which is 290. And here this will give us a change in internal energy of plus 94.28 kilojoules per kilograms. So we are providing a work of minus 124.7 kilojoules per kilograms to compress the air. As a result, we have an increase in temperature, an increase in pressure, and an increase in the internal energy of our air.